Hello and welcome to mini lecture number 27 on the definite integral. All right, before we begin in talking about what the definite integral is, it will be important that we cover some integration rules. So just like with derivatives, where most of how we take derivatives is by knowing some rules like the chain rule and the power rule, when we take integrals, what we really need to know is a bunch of integration rules. So we'll cover these in a little bit more detail in the coming lectures, but in order to use them, let's start by talking about a couple of important rules. The first of these is called the inverse power rule. So you're going to notice that these are the opposite of derivative rules, and so the first one is the inverse power rule. What is that inverse power rule? Well, it says if we're taking the integral of a power function, that we're going to raise the power by 1 and divide by that new power. So what we have here is we have x to the 5th over 5. Now, an important part of integrals is this unknown constant c. So every time we take an integral, we have to add an unknown constant c to the end. A lot of times this unknown constant will end up going away, but until it goes away, we have to add it in there. All right, so that's the inverse power rule. Similarly, if we have the integral of 1 over x, this becomes the natural log of x. So first of all, we have a 3 in here. Now, just like with derivatives, constants can be factored out of integrals. So the first thing that this gives us is x, 1 over x dx. Now we can use the integral of 1 over x as the natural log to get 3, the ln of x, plus this unknown constant c. Now, this is an unknown constant, so if we multiply that unknown constant by 3, it's still an unknown constant, so we can just redefine that unknown constant. And I'm just going to put a little prime on it to denote that it's not exactly the same as this guy. It's this unknown constant multiplied by 3, but this c prime has absorbed the 3 because it's still unknown. All right. Now we have the integral of e to the ax. If you integrate e to the ax, you end up getting out e to the ax multiplied by a factor 1 over a. All right, so let's do that. Here our a is equal to minus 2. So we end up by having 1 over that a times e to the ax, which our independent variable here is t. Now we also have to add that unknown constant c. Finally, we have the integral of the natural log of x. If you integrate the natural log of x, the answer is a little bit more complicated. Is x the natural log of x minus x. So just like with derivatives, we can extend this to taking the integral of any base log by first converting that base into the natural log using change of base rules. So we first start with this. Now notice that just like in a derivative, this natural log of 10 is a constant and it can be factored out. So we'll have 1 over the natural log of 10 times the integral of the natural log of x dx. All right, if we want to take this integral, we know what the integral of the natural log is, and so this becomes 1 over the natural log of 10 times x ln of x minus x plus some unknown constant c. Now, remember, this is an unknown constant, so if we multiply it by 1 over the natural log, it's still an unknown constant. So we have x ln of x minus x divided by the natural log of 10 minus some unknown constant that I'm now going to have as a c prime because it has absorbed that natural log of 10. All right, now note that when we take derivatives, we often think of 1 over things as negative powers, and so we could have done this as x to the minus 1 dx, and you might say, well, that's also a power. Why didn't I use the inverse power rule? Now, when you have the integral of x to the minus 1, it's very special because the inverse power rule is going to fall apart. And it's not going to work, so it has a special definition as the natural log of x. To show this play out, we could think of the integral of x to the minus 1 dx. What would this give us? Well, it would give us, by the definition of the inverse power rule, x to the minus 1 plus 1 divided by minus 1 plus 1, which is equal to x to the 0th. I have to add my unknown constant in there, divided by 0, and that blows up and doesn't work. So you can't divide by 0, so since the inverse power rule would lead to 0 in the denominator, it has to follow a different rule, and so that is the natural log of x. All right. So now that we have these basic integration rules under our belt, and don't worry about memorizing these at this point, just make sure that you have this table of integration rules ready when you need them. All right, so now that you have those integration rules, we can talk about what the definite integral is. So the definite integral is defined by the Riemann sum. So remember, the Riemann sum is the area under the curve as calculated by a whole bunch of little rectangles. So if we take the definite integral, it is when you have this Riemann sum where those rectangles get smaller and smaller and smaller and smaller until you're taking the limit as the little width of those rectangles goes to 0. All right, so if x1 is equal to a and xn is equal to b minus dx, then this is the Riemann sum that gives us the area of under the curve f of x between a and b. If we take the limit as the number of rectangles goes to infinity, we end up with this definite integral. Now, this is different than what we've had in the previous page because it has these limits of integration on the bottom and the top of the integral. So when we don't have these limits of integration, it's called an indefinite integral. So this here is called the indefinite integral. But when we add those limits of integration, it suddenly becomes a definite integral. So the first step of evaluating the definite integral is to actually evaluate the indefinite integral using those rules of integration that we had on the previous page. So the first thing we want to do is we want to pretend that those limits of integration aren't there and just try to take the integral, and then we're going to add a little bar on the end with an a and a b that says we're going to evaluate that integral between the points a and b. So to see what I mean, let's consider the definite integral of e to the x dx between 1 and 3. Now, that's a lot to pull off, so the first thing we're going to do is we're going to realize that this is the same as taking the integral, the definite integral of e to the x dx, and evaluating that integral between 1 and 3. So the first thing we have to do is we have to use our integration rules, which gives us this, and we want to evaluate that between 1 and 3. Now the thing is, I'm being a little vague here about what I mean by integrating between 1 and 3. So that's the part we have to do next. We have to evaluate the integration limits. In order to evaluate the integration limits between a and b, we first want to plug in the final value, the b, and subtract it from the initial value a. So what we end up here with is e to the 3, the final value, e to the 3 plus c, minus the integral of the first value, which is e to the 1 plus c. Now notice if I distribute that minus sign, I have e to the 3 plus c minus e to the 1 minus c. These are the same unknown constant, so they are going to cancel out. And we have e to the 3 minus e to the 1. All right, so when you do definite integrals, this integration constant is going to go away, but when you have the indefinite integral, the integral without the integration limits, you're going to have that integration constant, that unknown constant in there. All right, so let's practice this with a couple of integrals that illustrate the different properties of the definite integral. The first property that we have is just like a Riemann sum. The definite integral gives us the area under some curve as defined by the function between the points given by the integration limits. So the integral of x squared dx between minus 5 and 5 is the blue area shown here. In order to evaluate this, the first thing we have to do is we have to evaluate the indefinite integral, the corresponding indefinite integral. So if we evaluate that integral, we have x squared dx evaluated between minus 5 and 5, which, using our inverse power rule, we have this evaluated between minus 5 and 5. Plugging those values in, we have 5 cubed divided by 3 plus c minus 5 cubed, that whole quantity cubed divided by 3 plus c. Now, this plus c is going to cancel with that minus c, and if you plug this into your calculator, you're going to get the value 83.33. All right, so that is the first indefinite integral, this is the first definite integral that we're going to do, and it gives us the area under this curve. Note that this area under the curve is positive. It's all above the x-axis. If we have an integral where the function is partially above the x-axis and partially below the x-axis, just like with the Riemann sum, this part is going to be positive and this part here is going to be negative. All right, so if we look at this curve, it is given by the function x squared minus 9. If I want to take that integral, the first thing I have to do is I have to split up the integral on the minus sign. So just like with derivatives, you can split up an integral on the plus signs and on the minus signs. So another way of saying this is that the integral of a sum is the sum of the integrals. So a way of taking this integral is to have the integral of that minus the integral of that. Now this whole thing is going to be evaluated between minus 5 and 5. So we first do the indefinite integral, then we plug in the integration limits. All right, using the inverse power rule, you can take both of these integrals. So you end up with x cubed over 3 plus some unknown constant minus 9x over 1 minus some integration constant there. Notice that I have a minus sign here because of there, and I have a minus sign there because I'm distributing that minus sign. All right, these are two unknown constants. We can combine them into one unknown constant, so this whole thing comes out to being x cubed over 3 minus 9x plus some unknown constant c. Now we have to evaluate that on our integration limits between minus 5 and 5. All right, so that is the integral from here to here, but we can split that up as having the integral from here to here plus the integral from here to here plus the integral from here to here. So if I have the integral x cubed over 3 minus 9x plus c between minus 5 and minus 3 plus x cubed over 3 minus 9 plus c between minus 3 and 3 plus x cubed over 3 minus 9 plus c evaluated between 3 and 5. This gives us the first integral, the second integral, the third integral. Plugging in the numbers, I get 14.67 minus 36 and 14.67. So the area under this curve is 14.67, 14.67, and here in the red space I have a negative area of minus 36. All right. Note that because the area under the curve between a point and itself, if we have the same integration limit at the bottom and the top, so we are integrating from, for example, 5 to 5, then that comes out to being 0. A way of showing this is that we take the integral of this function. We first start by taking the indefinite integral. Remember that we can use change of logarithm rules to get this quantity here. We factor out the 1 over the natural log of 10 times the integral of ln of x dx. Then we use our integration rules to get this quantity here. Now we want to evaluate this whole thing between 5 and 5, between 5 and 5. So plugging in those integration limits, we have 5, the natural log of 5 minus 5 plus c divided by the natural log of 10 minus 5, the natural log of 5 minus 5 plus c divided by the natural log of 10. That all comes out to being 0, since this term is going to perfectly cancel with that term there. All right, so if we don't go anywhere, the area under our curve is 0. Finally, we have that if we integrate the area of a curve from a point 3 to a point 5, that is by definition negative of what we would get if we integrated from 5 to 3. So a way of showing this is we have this integral from 3 to 5 of e to the x dx. This comes out to being e to the x evaluated between 3 and 5, which gives us e to the 5 plus c minus e to the 3 minus c. These two cancel out, so we have e to the 5 minus e to the 3. All right, now if we did it the other way, so we integrated from 5 to 3 of e to the x dx, we would have e to the x plus c evaluated between 5 and 3, which is e. Now you plug in the upper limit first, so you have e to the 3 plus c minus e to the 5 minus c, which gives us e to the 3 minus e to the 5, which is the opposite, negative, of what we got there. All right, the fifth property is that if we have a constant in our integral, then that constant can be factored out. Another way of saying that is if we take our original blue function here and we multiply that blue function by a constant to get the red function, then the area just multiplies by that constant. So in order to take the integral here, we can first start by factoring out that 2. So then I have the integral of 2 times 1 over x dx, which is equal to the natural log of x plus c, evaluated between 3 and 5. So I have 2 ln of 5 plus c minus ln of 3 minus c. These cancel out. So you have 2, the ln of 5 minus the ln of 3, which is twice what you would get if you did the integral of the blue curve. All right, the sixth property that we have is that if we have this integral of the sum, then that can be split up on the sum. Another way of saying that is if you have the blue curve and you have the orange curve, if you add the area of those two curves together, you'll get the area under the green curve. All right, so we have here x squared over 2 plus c evaluated between 3 and 5 plus x cubed over 3 evaluated between 3 and 5 plus a second integration constant, which comes out to being x 5 squared over 2 plus minus 3 squared over 2 plus 5 cubed over 3 minus 3 cubed over 3. All right, so that is some integration rules, and with that, I'll let you try to tackle the self-study question where you're going to have to evaluate a definite integral on your own.